Printed circuit boards, also called PC boards, are simply PCBs that are everywhere, in systems as large as complex as the International Space Station, all the way down to devices as tiny as an implantable biomonitor. PCBs are in robots on Mars and aquatic cameras at the bottom of the ocean. They're in cars, light bulbs, and even clothes and food packaging. Regardless of size and application, every one of these boards went through a similar design process. Hi, I'm Dwayne Benson from Screaming Circuits, your presenter for today. I'm here to talk about the fundamentals of printed circuit board design. I'd like to share my thoughts on that design process and help you get started. Even if you aren't new to PCB design, this course should help you avoid a number of common pitfalls and create better, more reliable designs. The PCB is a board usually made of a fiberglass-like material with copper traces on and embedded in it. The board material acts as the mechanical structure and insulator, and the copper makes up the electronic circuit. Components are attached to the copper on the board using various soldering techniques. PCBs can have as few as one copper layer or as many as several dozen. The layers are connected with vias, which are holes drilled all or partway through the board and plated with copper. The copper on the outside layers is usually coated with a different metal such as solder, silver, gold, or tin to improve its solderability and reduce the chances of corrosion. The areas of copper that don't need to be soldered to are usually covered with a non-conducting ink called solder mask. Reference information, labeling, and identifying graphics are printed with a silkscreen process or, in smaller quantities, with an inkjet printer. During this class, I'll usually refer to the metallic surface as copper, even if it's plated with another solderable material. Through-hole components have leads that extend through the PCB and are soldered from the opposite side as the component. Surface mount components sit on and are soldered to copper pads either on the top or bottom surface of the PC board. Modern PCB designs tend to use most or all surface mount components, also called SMT or SMD devices. Surface mount devices are smaller, less expensive, and easier to handle with automated manufacturing equipment. In some cases, ultra-small components such as resistors and capacitors are even embedded inside the board material. Printed circuit boards come in as diverse a set of characteristics as there are applications. Boards can be made from different substrate materials, such as the old brown phenolic, many different fiberglass-like materials, bendable flex, and even ceramic or insulated metal. Some of the common terms you'll hear used to describe PC boards are rigid. This refers to most standard types of PCBs. They are structurally stiff enough to hold the components with minimal movement. Flex. This is a thin, very high-temperature plastic, usually polyimide. It's used when the circuit has to conform to a non-flat shape. For example, cameras have flex circuits that wrap around the lens, motors, and batteries. Rigid flex. Rigid flex has small rigid circuit boards connected with flex material. These are used when mechanical structure is still important, but space is at a premium and some bending is required. Cell phones and wearable devices often use rigid flex. High speed. These substrate materials are designed specifically for very high-speed digital and RF applications. Once into the gigahertz range, signal integrity becomes challenging and every factor can become critical. High-speed substrates may be required with such designs. Ceramic and metal core. These two materials are used in very specialized applications, such as high-temperature settings. They have a layer of ceramic, or metal, usually aluminum, bonded to a more conventional PC board substrate. For example, most high-power LEDs use metal core boards. Often there will be a small metal core board for the high-temperature component connected to a more conventional PC board for the rest of the electronics. Like any other type of project, the process of designing a printed circuit board is governed by three opposing axes: cost, schedule, and performance. If you want more out of one axis, you'll have to take something away from the other. For example, if you need lower cost, you can slide up the schedule or drop some features. If you need it faster, You'll have to spend more money, and so on. Fortunately, the electronics industry of today has given us a lot of extra flexibility in this area. Offshore manufacturers give you low-cost options if you can spare the time. Fast-turn manufacturers like mine allow you to get everything done quicker if you have the budget. Even better, highly integrated chips may allow you to increase performance while reducing time and cost. The design process starts with 4 primary inputs: the bill of materials, the schematic diagram, your mechanical constraints, and environmental and regulatory requirements. At this point in time, you will also want to know a good deal about your budget and schedule requirements and available resources. The bill of materials, called the BOM, is a list of all of the components to be placed on the PCB. The file typically includes an index number, the number of times a specific component will be used on the board, the reference designator from the schematic, the component manufacturer, and the manufacturer's part numbers. If a specific component is used more than once, a common bypass capacitor, for example, it will still only take up one line in the bill of materials. One field in the BOM will list the number of times the component is used, and another field will list all of the reference designators for that part number. For example, take a look at line 5 in my BOM on this slide. It's a 0.1 microfarad 10-volt capacitor. The first field in the table has a light item index 5, because it's the 5th unique part number in my BOM. The next field has a quantity of this component used on the board, which is also 5 coincidentally. Field 3 holds reference designators C1, C2, C3, C4, and C5. The next field has the manufacturer, and the final field has the manufacturer's part number. You will likely have additional fields, such as the distributor part number, the description, the package type, and other tidbits, as I have here. But the first 5 columns in this example shows what is generally considered to be the minimum data set needed for a good bill of materials. Note that down at the bottom, I have 3 lines which are highlighted in red and with the label DNS over in the type column. DNS means do not stuff. That's an instruction to your manufacturer to not install that component during the assembly phase. Some people use DNP for do not place, or DNI for do not insert. It's always best to consult with your manufacturer to get their preferred labeling. You may also want to include alternate parts for components that are likely to go out of stock. Passives like capacitors and resistors are notorious for going out of stock without notice. Invariably, though, there will be half a dozen nearly identical parts that will fit the bill just as well. Create an alternates list so your purchasing folks or manufacturer won't get stuck not knowing if the substitute is valid or not. The schematic diagram shows all of the components using symbols and functional blocks. It shows all of the interconnections between the components and is a visual representation of the workings of the entire circuit. The schematic is created before the layout starts, and depending on your PC board CAD layout software, may be used in 2 ways. Some CAD systems will allow you to easily switch back and forth between the schematic and the layout portions of the software with tight coupling. Add or remove a component in the schematic and it will be added or removed to the CAD layout. In other CAD systems, the designer will need to generate what's called a netlist from the schematic. The netlist is a machine-readable version of the schematic with all of the components and the interconnecting wires, or nets, detailed in a form that the layout software can recognize. Systems using the netlist method of data transfer to the layout software are more loosely coupled. They will require more careful change management than do tightly coupled systems. Some PC boards exist as a standalone board without much concern for size or where to put things, but those are pretty rare. In most cases, the PC board has to fit in a mechanical enclosure or connect to another board, as is the case of the example shown on the slide. Mechanical constraints such as bolt holes, board outline, and connector positions may have a significant impact on the layout. Requirements for a smaller board may force you to increase your layer count, put parts on both the front and back, shift to a multi-board set, or even in some cases may require you to reduce the product functionality. Before starting your layout, make sure all of these details are clearly understood and well documented. Environmental and regulatory requirements are another significant set of factors that often get the afterthought treatment. Safety agencies will require minimum component spacing for high voltage components and traces. If any of your components run hot, you will need to consider thermal mass, airflow, and cooling. High-speed designs need extra care in layout or extra filter devices to keep EMI, crosstalk, and signal degradation to a minimum. Lead has been banned in most electronic circuits outside of the U.S. for the better part of a decade now, but there still are a number of leaded components in use. Unless your product is exempt from the RoHS, or Reduction of Hazardous Substances, requirements, you'll need to ensure that whatever components you pick are RoHS compliant. Mixing leaded and lead-free is never a good idea. Some exotic applications still require leaded solder, but most new BGAs only come in lead-free versions. Now is the time to sort those issues out. With all of the requisite inputs in hand, you may feel ready to go, but you're not quite there yet. Taking care of these intermediate steps now will make for a smoother process once you get deep into the layout. The core of this part of the process, creating or locating the library components, setting up the layer stack-up, and defining and setting the design rules can be done as you go during layout. In fact, many people do just that with smaller projects. However, putting the extra time in here will help reduce errors before they're made and will give you more time to answer any difficult questions that may come up during layout. Finally, careful use of design rules-based layout with the design rules defined now can eliminate a lot of busy work that would otherwise come up during routing. While the schematic details the components and their interconnections, it doesn't contain information about physical size and pinouts of each component. This information is contained in the component CAD parts library, also called footprints or land patterns. The footprint has all of the information needed to place the part on the board, run circuit traces to it, and solder the part onto the board during manufacturing. It has the physical size, the outline, the copper layers, reference designator, solder paste and solder mask openings, and pin 1 indicator. The footprint is one of the most important parts of the layout process, though it also ends up as an afterthought. There are so many variations in package design and so many critical factors today that footprints simply can't be taken for granted. Many footprints these days can be found crowdsourced or in dusty libraries that came with an older version of CAD software. All of those should be suspect. Unless you've used the footprint before or acquired it from a known reliable source, double-check the copper sizes, the solder paste openings, and all of the pin connections. You won't regret it. The layer stack-up details the order in which the PC board copper layers go, from top to bottom. It's used by the PC board fabricator to ensure that all of your traces and vias connect where they're supposed to. This example shows a 4-layer board with the internal layers used for power and ground planes. The stack-up can get quite complex as layer counts go up. Traces and via specs and design rules are used to help automate the layout process and ensure that your PC board can be successfully fabricated. Your design rules will be a crossover between what you need and what your fab house can produce. Some more primitive CAD software will require that you manually pick the width for a via or copper trace if you want it to differ from the default. Other software will let you set up a series of design rules and will pick widths based on those rules. For example, you might specify that power and ground traces are 16 mils in width and standard signal traces are 8 mils wide. The CAD system would then default to those widths when you picked a net in that net class. The net is the connection, like from pin 7 of chip U2 to pin 1 of capacitor C3. The net class would be the type of net, like power, ground, or signal. Like the footprints and layer stack, you need to determine these rules after you've created the schematic, but before starting the layout. You'll need to refer to your fab house, both to ensure that they can build what you need and to get the final say on their design rules. Some fab houses even have downloadable design rule sets for various CAD packages. That makes setting things up a lot easier, but you still have to choose your net classes and pick the sizes for your particular traces. Getting into the basic layout, your first step is going to be the board outline. You'll need to set up the mechanical portion of the design, which is the outline and any fixed mounting holes. The board outline is usually drawn in the dimension layer, sometimes a layer called milling is used. Check the documentation for your CAD software to see if you are unsure. The milling or dimension layer will also be used to indicate slots or cutouts in the board. Mounting holes are not necessarily the same as large vias. Vias will be plated through with metal. If you need the mounting hole to be plated through, for a ground screw, for example, use a via. Just make sure the hole doesn't exceed your board fab company's maximum via size. Otherwise, use the unplated hole component from your CAD parts library. In my example, I've drawn a round board with a small flat area for a USB micro B connector down near the bottom. I have 5 1/8" mounting holes. The floor plan comes next. With the mechanical constraints in place, your next step is to arrange the components on the board. That's called the floor plan. This is a very important step as it will affect just about everything, from routing to manufacturability to long-term thermal performance. Here I've got some of the components placed and a lot more still to be placed off the surface of the board. The thin lines between the parts are called unrouted air wires. They represent the connections between the pins of all of your parts that have not yet been routed. The collective set of unrouted air wires is referred to as a rat's nest. Now contrast the top and bottom images in this slide. With the connectors in place, as in the top image, I'm going to have a much more complex routing problem. I'll end up with a lot more vias and use up a lot more board real estate with traces. In the bottom image, look how simpler the air wires go. I've moved a few connectors around and rotated the microcontroller. You can see that the rat's nest is a lot cleaner and will lead to a much simpler routing job. You may have to go through a few iterations of moving components and rotating various parts to end up with optimal arrangements. Bypass capacitors for ICs need to go as close to power and ground of the chip as possible. Some chips give very specific instructions on where to place the capacitors and other supporting components. Read the data sheet and follow those instructions. When in doubt, always read the data sheet. Some components, like USB interfaces, may have restrictions on the length of traces and may need equal length traces. Again, read the data sheet. It's far easier to spend a bit of extra time reading now than it will be to debug a problem board later on. Design rules don't always cover everything. If your footprint is fully formed, they'll have what's as a courtyard or keep-out zone. Basically, this shows the minimum distance between components or between a component and a pad and a via or trace. Your CAD package should have default minimum spacing, but not all do, and not all footprints have keep-out layers filled in. If you don't have keep-out data, check the data sheet or use a similar component for a close approximation. If there's a big size mismatch between two components, you may need to increase the distance. I'll talk about that a bit more in the next slide. Now is a good time to consider thermal issues as well. High power components need room for airflow. They may need room for heat sinks or fans as well. refer to the heatsink and airflow guidelines published by the power components manufacturer. Heat isn't just an issue for operation. It can also have a great impact on the manufacturability of the board. The center image illustrates a large surface mount component, maybe a tantalum capacitor, next to a very small component, like an 0402 size resistor. The thermal mass of the big capacitor will act as a heat sink during manufacturing and keep the solder on the near pad of the resistor from melting as fast as the far pad. The surface tension of the melted solder on the far pad may pull the component up vertical in what's called tombstoning, because it looks like a little tombstone. Even an inside layer of copper under one pad and not the other pad can cause this problem. Image A shows another common layout-caused manufacturing problem. The big metal can capacitors have a lot of thermal mass. The solder on the contacts between the capacitors won't melt without a little extra time in the reflow oven. However, that extra time in the reflow oven overtemps the capacitors, even though they're rated for the Rojas temperatures, and destroyed them. You may need to spread them out or add more room between them, as in the image on the far right. This design has 12 RGB LEDs arranged around the board that will act as the hour hands on a digital clock. I've done two things here. First, I created a triangle with all the correct distances and drew it in my CAD software's document layer. The document layer looks just like a silkscreen layer when visible, but it won't be printed on the board. You can use this layer to put in extra information for yourself or for the manufacturer. You may also notice that I wrote in the documentation layer, "No tabs here," down near the bottom. That's an instruction to the PC board fabrication house not to put a panel tab where the micro USB connectors go. If they did put the panel tab there, the board wouldn't be buildable when panelized. Some people create a fabrication documentation layer and a separate assembly documentation layer. An example might pertain to reference designators. If the board is too compact for reference designators, or if for aesthetic reasons you want to leave them off the finished board, you can put the reference designators in an assembly documentation layer. Then be sure to let your assembly house know what you've done. The other things I did here is keep all of the LEDs aligned with the baseline of the PC board. In theory, you can place a component at any rotation angle you want, but like any system, manufacturing works better when there are fewer variables. You reduce the probability of error if you keep your components aligned at factors of 90 degrees. It also helps to keep polarities of polarized components oriented the same way as much as possible. For example, if you can, have all of the diode polarities on the board facing in the same direction. After component positioning, you'll need to look at power and ground distribution. With a two-layer board, your options are limited to individually routing power and ground, or using a polygon fill, also called a flood or a pour. For simple low-speed layouts, it's common to route power just like any other signal. You'll typically use a wider trace, which you can set manually or with design rules. Drawing a polygon in the board shape and giving it the same name as your power or ground signals may make the job easier. Keep in mind, though, that you can end up with parts of a ground plane that are disconnected from the rest of the board. This is called an orphan. Some CAD error checks will spot such a problem and some won't. If you have a 4 or more layer board, common practice is to designate one of the layers for ground and one for power. Doing so can leave more room for signal routing, can reduce EMI, and can have a cleaner looking and easier to debug board. It can also reduce the chances of having orphan ground or power areas, as I warned against in the prior slide. While the basic purpose of vias generally stays the same, they come in a number of different forms. In the drawing, vias B and D are standard vias that go completely through the PC board. These are the most common and least expensive to produce. A is a blind via, as in blind from the other side of the PC board. It goes from the surface on one side to an internal layer and not all the way through. Blind vias can free up the space for routing on internal layers and on the other side of the board. They can also help with signal integrity. C is a buried via. It goes between two internal layers and again can help free up space for routing on other layers. E represents a standard via that has been filled and plated over. Open vias in solder pads are always a bad thing. Solder will be wicked down the via, leading to solder on the other side of the board and often an insufficient solder joint on the top. Vias in pad are sometimes necessary with very compact layouts or fine-pitch BGAs, and having the pad filled and plated over at the board house, as I've shown here, is the most reliable method for using a via in pad. Some specific component challenges, BGAs for example. In the past, BGAs came with pads as far apart as 2 millimeters on center. With large pitch like that, you can often route one or two traces between the BGA LAN pads on the surface of the board. Most newer BGAs come with 1 millimeter or smaller on-center pitch LAN pads. That makes routing between the two not likely to be possible. It leaves vias in or between the pads as your only options. Down to about 0.5 millimeter pitch pads, you can place the vias between the pads in a dog bone formation. You must have solder mask between the pad and the via, otherwise the solder will migrate towards the via, leading to a poor solder connection or no connection at all. For BGAs with smaller pitch than 0.5 millimeter, you will need to put all the vias in the pads and have the pads filled and plated over at the board house, as shown in the illustration on the left there. Those are vias. They've been filled with a conductive material and then plated over with metal at the board house. The BGA needs to have a solid, flat surface to adhere to. QFN and DFN, quad flat pack no leads or dual flat pack no leads, packages have been common for about a decade or so, but they still pose some pretty big challenges in layout. First of all, like a BGA, their leads are under the part, so it's difficult to inspect. Second, many have a big metal pad in the center. That big pad, if not treated properly, can cause a lot of manufacturing problems. If the opening on the solder paste layer in the part footprint is wide open, as is often the case, you will likely end up with too much solder in the center. The part will float up on that excess solder and may leave the side pads unconnected. Even today, many of the footprints that you get from the manufacturers will still have that wide open center. Always inspect the footprint for a QFN, even if it comes with your CAD package. Depending on the type of paste squeegee used in manufacturing, the opposite can occur too, leaving a large area under the part void of solder. The solution is the same for both cases. Segment the solder paste layer so that 50 to 75% of the pad is covered with paste. Some high-power QFNs may require thermal vias in the center of the pad. If that's the case, the best option is to have the pads filled at the board house with a thermally conductive material and plated over with metal. You can often get by with more conventional vias in the pad of a QFN, capped with solder mask, as shown in the illustration lower left. Just make sure that you put the vias in the areas that will not be getting solder paste. On the diagram on the image on the right, you can see a large QFN, the little square hatch marks. That's the solder paste openings in the stencil layer. So I've reduced the amount of solder that will go into the center pad there. Many high-speed designs come with special advanced trace requirements. High-speed devices often use differential signals. These are pair signals, with one being positive and one being negative, equal and opposites. Having equal and opposite signals helps to reduce the problem with ground bound. You may need to find a specialized reference or trace width calculator to determine the optimum trace width and separation based on the signal speed and distance traveled. You may also need to keep these traces as parallel as possible and as close to equal length as possible. Some high-speed designs require controlled impedance routing and PC bar material. That's beyond the scope of this class, but be aware that if you're getting up into the high megahertz and gigahertz, you may need extra help or expertise. Power traces may need to be made extra wide or even with heavier, that's thicker, copper plating to carry the necessary current loads. Even with relatively low current designs, if your power source is a long way from the component, you may need to widen the power trace to prevent excess voltage drop. In days past, parts could be programmed and tested with clip-on equipment. With today's super small and leadless surface mount components, that's no longer possible. For large production volumes, the surface mount programmable parts can be programmed at the factory or distributor prior to manufacturing. However, adding a programming port will allow for reprogramming or post-manufacturing programming. Many microcontrollers can operate bootloaders, allowing for reprogramming over a USB or serial port. You may also need to add test points, as it's virtually impossible to test leadless parts. Test points can be small copper pads or full through-hole header spots, as I've shown on the image on the right there. It's not uncommon to add the test points for the prototype phase and then remove all or most for volume production. To auto-route or not to auto-route? That is the question. To this day, there are very strong opinions on both sides. But CAD companies are putting a lot of time and effort into their auto-routers. They're getting better all the time. Whether you use an auto-router or not, time you put in before routing, setting up the design rules will make the job easier and the routing more accurate. The best option is probably a combination of auto-router and hand routing. First, route your power and ground. Next, any critical signal paths. For example, high-speed traces often need extra care in their routing. You might want to hand route some signals that are very important, very critical first, then either auto-route or hand route all of the less critical signals. Finally, go back and double-check everything. Don't just rely on a DRC, stands for Design Rule Check, or ERC, Error Rules Check, functions built into your CAD software. The DRC and ERC can catch a lot, but they won't catch everything. Those check functions may not catch isolated power and ground orphan areas. Look at my components D3 and R6. That passed the design rule check, but it still may lead to problems in manufacturing. With small 2-lead components, it's important to have the same width traces coming out of both sides. Otherwise, the extra thermal mass on the side with the thicker trace can slow the melt and cause the component to tombstone or to move off the pad to the side. Make both traces the same. You can always change the trace width once you're away from the component if you need to. Design rule checking. Some CAD systems essentially perform a DRC, design rule check, as you go. They won't let you create a board that violates design rules. Some require that you periodically run a DRC as a separate operation. You may have to set all of your design rules manually or download a DRC file from your board fab house. Either way, the DRC check will make sure that you don't design a board that can't be fabricated at your chosen fab shop. Don't leave out the manual checking, though. A DRC can't find everything. Your traces are the meat of your PC board layout. Now that you've put them all down, either with the auto router, by hand, or both, it's time to examine your work closely. And I do this both before and after running a DRC check. When looking at the traces, it can be helpful to turn off all of the other layers. I like to isolate each layer individually, leaving the vias and through holes added in. This allows me to give each individual layer a good close look for any oddities like unnecessary bends, overly long routes, poorly constructed connections, or incorrectly sized traces. 90-degree bends in your routing should be avoided. Do your best to make all trace connections at 45 degrees. This isn't as important as it was in the past, but it still decreases the chances of a break at a corner. With the vias and holes still visible, you can move traces around quite a bit without risking messing up something on another layer. Make this check for every single signal layer as well as your ground and power planes if you have them. Few people opt for boards without solder mask these days. In some cases, it can reduce your board fab costs, but it can lead to so many other problems down the road. I'm just going to say always have solder mask. Always. You might think that since manufacturing is automated these days, the silkscreen would be optional. That it wouldn't matter if your board has reference designators or not. In theory, that should be true, but there's still a lot of human work involved in the process and too much ambiguity due to poor use of standards and marketing by component manufacturers. Either have a clear silkscreen on your board or create an assembly drawing that has all of the information on it. Diodes deserve a special call out for silkscreen because there's so much variation in the way they are marked. It's pretty common for designers to mark a diode with a plus or minus sign. That might seem reasonable, except that Zehners and barrier diodes are often backwards from that. Chain diodes can also end up with either end connected to plus or minus. Use a diode symbol if you have room. Not just the triangle part, use the whole symbol. You can also use K for cathode or A for anode. Make sure there's no ambiguity whatsoever. Panelizing your boards will allow for faster and more efficient manufacturing. Most design and manufacturing type folks wouldn't dream of sending a 2-inch by 3-inch PCB out for high volume manufacturing as a single board. It would generally be replicated up in a panel, also called an array by some people, size that would fill the volume manufacturer's equipment and would yield the largest number of boards. In most cases, you'll provide a single, also called one-up, board designed to your fab house. The fab house will replicate the design and produce it in a larger panel. You don't need to do anything except specify the type of panelization and find out what your assembly house needs. The two main types of panelization, first, V-score. It's created by running a V-shaped blade across the top and bottom of the panel without cutting all the way through it. The image in the middle towards the bottom of the slide shows V-score. The other type is called tab routed. The boards are separated with a router bit, leaving just small tabs that can be easily cut or broken away. The image lower right shows a close-up of a panel tab. This example also has small drill holes to allow even easier separation with less mechanical stress on board. Those are called mouse bites. Fiducials. A fiducial is essentially an alignment mark for surface mount assembly machines. High volume assembly requires them to ensure accurate registration and parts placement. The basic idea is to create a non-reversible pattern with 2 or 3 fiducial marks on your board or panel. As you can see in the image on the left, the designer placed 3 fiducials around the board in a non-reversible pattern. In terms of the specific construction of a fiducial, there are 2 things that are most important: contrast and accuracy of position. You get the contrast by making it from bare copper. Make it a 1 to 2 millimeter diameter circle. Don't cover it with solder mask. Make the mask opening 2 to 5 times larger than the copper. The image on the right shows a close-up detail. This particular fiducial mark uses a square cutout in the solder mask. Most use a round cutout, but the shape isn't all that important. The copper pad should be round, though. Making it out of copper gives positional accuracy. I've been asked why silkscreen markers aren't acceptable. Well, silkscreen isn't always registered consistently and is therefore won't ensure accurate alignment. Don't use silkscreen as a fiducial or a positioning mark of any kind. You're almost done here and to one of the most important parts, the design outputs. Finally, we have the ultimate target, the design output files that you'll hand off to a manufacturer. Basically, the design process outputs need to take your work and deliver it who a manufacturer in a form that they can use. I've already described the bill of materials. You'll need that, of course, so your manufacturer or in-house purchasing folks can buy the correct parts. An important note on bills of materials is that quite often, between the start of the design process and completion, a few of the parts you may have picked may have gone out of stock. Always go through the BOM again to verify availability and pick substitutes as necessary. Traditionally, manufacturing has taken what are known as Gerber files, a drill list, and a pick-and-place file, which gives the XY location for each part, as well as the rotation inside of the board, and fab and assembly drawings. Virtually all CAD layout software output these files. The Gerbers are a set of files used to create the various layers of the PC board. Each layer requires an individual file, so a 6-layer board, 6 copper layers, will typically require at least 13 distinct files, one for each copper layer, top solder mask, bottom solder mask, top silkscreen, bottom silkscreen, drill holes, solder paste layer for the top and bottom if the board has SMT parts on both sides. That's a lot. The drill file is combined with the Gerbers to line up the via and through-hole component holes with the appropriate spots in the PC board. Then the pick-and-place file will tell the assembly house where to put each component, what angle to place it at, and which side of the board it goes on. Fab drawings hold a human-readable, often in PDF format, description of the board and any special instructions that are needed by the fab house. The assembly drawings would be the same, but for the assembly house. I cannot understate the importance of fab drawings and assembly drawings if there's anything that needs any clearing up in your design. Sometimes the parts are too densely packed for the reference designators and polarity marks to show up on the actual board, or for aesthetic reasons, the designer doesn't want them on the board. In such cases, all of that information would be put into a set of assembly drawings, PDF files showing all of the necessary reference information. In a perfect world, that all works fine, but we don't live in a perfect world. The Gerber file goes back to the mid-1970s when PC boards were fabricated with a largely manual process. The files are lists of ASCII commands that essentially create a 1-bit per pixel bitmap of each layer. Newer manufacturing file formats, ODB++ and IPC 2581, are starting to be used. These two formats promise to contain a much better set of instructions for the board fab shop and assembly house. The ODB++ and IPC 2581 file formats, as of this writing, still aren't universally accepted, but are getting more and more so all the time. Use and promotion of these new intelligent CAD output file formats helps to reduce the number of manual steps in human interpretation and will eventually lead to better quality and faster manufacturing times. If you can use the ODB++ or IPC 2581 file formats, please do. Contact your fab house and manufacturer first to make sure they can handle them, though. Finally, we've got your finished product. If all has gone well, you'll end up with a working board ready to power up and test. Hopefully it all works, but more often than not, a change or two will be necessary. If you haven't already, start working with your volume manufacturers to make sure they can easily build your board. They'll usually have a number of recommendations that will reduce the cost or time to build or improve reliability. Thank you for your time today. I hope you found this course valuable.
Designing today's printed circuit boards requires more of engineers than ever before. Proliferation of ICs in small leadless packages and increasing demands for fast, high-bandwidth interfaces results in dense, complex layouts. High-speed circuitry mandates repeatable, interactive routing with real-time design rule checks and advanced constraints. Successful product creation demands seamless collaboration between ECAD and MCAD tools in 3D. Can your PCB tool tackle these next-generation layout challenges? Many electrical engineers are not familiar with the physical implementation of printed circuit boards, but are now taking on that responsibility. A schematic-driven process ensures that all the components, connections, and design rules are passed to the layout and stay in sync with your design through real-time data synchronization. Driving placement from the schematic, where an engineer is familiar with the design, ensures proper grouping of the components. Many of today's designs have a complex set of constraints that must be maintained, such as minimum or maximum lengths, matched lengths, and differential pairs. Having an easy way to create and manage these constraints, as well as having interactive and automatic routing that will adhere to these constraints as interconnects are completed, is a necessity. Routing is a complex task, so it is important for engineers to have information displayed in real time as they complete their designs. To truly visualize the end product, a 3D design environment that shows the electrical components and allows mechanical parts to be imported, displayed, and subjected to full design rule checking for conflict detection is needed. Realize your next generation electronic products by choosing a cutting-edge platform that lets you focus on realizing your vision. The PADS product creation platform can help you manage the complexities of modern PCB design so your products get to the market and work correctly the first time.